Welcome to the 13th lecture from chapter number 7. We are studying VLSI Design, and in this lecture we'll study about the transient analysis of NAND gate. In our previous lecture we studied how to draw the schematic of a NAND 2, NAND 3 or 4, and for any Boolean expression given this Boolean expression we can draw. Given a Boolean expression, we studied how to draw the schematic in our last lecture. So this is the schematic of an NAND 2 that we studied in last lecture. We have two MP transistors, the PMOS transistors connected in parallel, and two NMOS transistors connected in series. And we studied some basic scheme or basic technique to draw these schematics in our last lecture 7-12. Right, so given this, we see that we have one drain capacitance Cp at the output. We have one other drain capacitance for this MP. Let's call it MP1, MP2, Mn1, Mn2. So this is Cp corresponding to this MP1. This Cp, the drain capacitance, is corresponding to this second transistor MP2, and this Cn corresponding to this Mn1. But the drain capacitance of this transistor doesn't contribute to the output terminal. And here we have this Cl, the load capacitance. Right, so we studied that all these transistors that are internal to the gate, we called them CFET in our last lecture. And Cout is put equal to CFET plus Cl. So CFET is 2Cp plus Cn in this case, whereas in case of an inverter and not, we studied that CFET was equal to Cp plus Cn. Right, so and we also studied in case of not that Tr is 2.2 tau p. This is a recap from one of our previous lectures. We studied Tr is 2.2 times tau p, where tau p is RPC out, where Rp is the total resistance offered by this PMOS array. That is why I have written it capital P instead of small p. In case of a not, it is small rp, but in case of this gate, this is R capital P. So the worst case delay would be when we have only one of these two parallel transistors on, either this one or this one, but not both. So that will offer a resistance equal to the resistance offered by a not, R small p, C out. And the best case delay would be when these two transistors, they both are on. This means they will offer the least possible resistance, Rp by 2, because they will be in parallel and the resistance offered will be cut to 1/2. Right. For the fault time delay, we studied in one of our previous lectures that it is 2.2 times tau n, where tau n is Rn, the equivalent resistance of NMOS array. This is capital N. Right, this capital N is equal to 2 times Rn. Why? Because when this array is on, there is only one possibility. There is only one possibility that these two transistors, they both are on. So therefore it is 2.2 times 2 Rn times C out, because when this array is on, this array is on only when both these transistors are on. And if they both are on, there will be two transistors in series, the resistance will be doubled, 2 times Rn. So the best and the worst case time delays are equal in case of the fault time. Right, that's all for this, and in the next lecture we will study transient analysis of node 2. Right, thank you.